All right, welcome again, everyone, to my channel. We're going to be discussing today something called piecewise functions. And the objective is, so normally in American high schools, you cover piecewise functions in the subject called Algebra II. So that's why I've titled the video Piecewise Functions, Algebra II topics. If you studied math in another country, I know the sequence is a little bit different. So, but because most of my audience is US based, I'm trying to, I've labeled it in this way so that they know where I'm coming from with that. So, but it's really an algebra topic. And we're going to be in today's video discussing how to deal with a piecewise function. A function defined by parts, in other words. And so what I'll do is, first, we need definitions. I am assuming those of you watching this video that you have, that you are taking Algebra II. If not, you may cover it sometimes in Algebra I, but it's not very common. So it really depends on your school and your district. So I'm assuming Algebra II, although I do cover it in my classes for introductory algebra as well. So most of the functions you've studied so far, they have a single rule. And one rule is applied to every valid input. So for example, if you had the function f of x equals 2x, that means that you double anything you put as x, right? Any input, right? You have in a function, you have input, output. So we are going to look at a function that apply different rules to different inputs, as well as some functions that require special notation to denote the rules that they represent. So you'll see several new types of problems, but your key strategy for solving them should not be new. When you are working with an unusual expression in a problem, you try to find ways to convert the problem into one involving expressions you know how to handle. So first, let me see if I can share with you. We'll try, they have a new feature now. All right, so you should be able to see a board. And what we'll do is a piecewise defined function. So we've already said that functions are machines that take an input and you produce an output according to some rule, right? It's really a machine. So you can also imagine a machine that applies different rules to different inputs in order to produce an output. So that's what we call a piecewise defined function. And when you describe a function, you have to both give the rules used to produce the outputs and describe when to apply each rule. So as an example of that, let's do a basic one. It sort of looks like this. You will have f of x equals, and then you'll have, usually the notation we use is the braces. Let's do 2, so 2x will apply 2x if x is less than 0. And let's do 3x if x is greater than 0. All right, now, so what we're saying here is we have a function that doubles negative inputs, but triples positive inputs. So if your input is greater than 0, it's going to be positive. So that means you're going to do 3x. If your input is less than 0, in other words, a negative number, then you're going to do 2 times x. Notice that f of x is not defined for x equals 0. I only put less than 0 or greater than 0. So that means that because it's not defined for 0, 0 is not in the domain of f. Okay, very important. And this, by the way, I'm just kind of jumping ahead a little bit, but this is, you can analyze limits of functions in calculus, for example. This is kind of the foundation of it, because we're going to talk about continuity in this video. So let's do an example where we're going to let g be the function defined for all real numbers. So I'm just going to show you. So this is what it looks like. This is an example of a piecewise function. That's how you know it has braces. It tells you the constraints. And then let's see, we can do. To erase this. Okay, this time I'm going to say g of x and what we'll do is g of x we'll say is 2x if x is less than 2. And we're going to say that it's going to be 2 to the x if x is greater than or equal to 2. Okay, so first let's compute some values, right? Let's say g of 0. And again, I'm assuming you've done functions before, that you have fog and golf and all that. So if you haven't, then you should not be watching this video. So this is g of 0. So because we have not, we're saying that it's either less than 2, so 0 works, or greater than or equal to 2, right? So if it's a g of 0, that means we need to compute it for 2x. So that means g times 0 becomes, so you use substitution. So that's 2 times 0, plugging it in for x in the 2x, and that's going to give you 0. Okay? And let's see, g of 1. Well, g of 1 also works for 2x, right? So g of 1 is going to be 2 times 1. These are just examples I'm drawing from. And then that's equal to 2. Okay? And then if we have g, let's say g of 2, well, in that case, right, you have 2 squared, right? You can't use the 2x. You have to use 2 to the x, because at that point, the constraint is that it's if it's greater than or equal to 2, you're going to do 2x, 2 to the x. So if it was 2, you do g of 2. 2 to the 2, which is going to give you 4. Okay, and I could go on and on with this. I think you get the point. So if you graphed it, right, we're going to figure out if we graph g of x. Okay, so here we have a situation in which we know that x is less than 2. So we need to graph g of x equals 2x. For all values of x that are less than 2, the graph of g, you would see that it's the same as the graph of y equals 2x. In a similar vein, if it's x is greater than or equal to 2, you would have 2 to the x for all x greater than or equal to 2. So the graph of g would be the same as the graph of y equals 2 to the x. So if you graph y equals 2x and y equals 2 to the x, you would produce a graph that's, if you have a graphing calculator, but it's pretty much going to look like a, let me see if I can actually draw what I have in mind. All right, so on the coordinate plane, you would have a line that sort of goes up, and it would kind of look similar to, let's do, excuse my straight lines, but it should be a straight line. And then sort of goes like that in a way. All right, we'll put a little arrow here. Okay, so that means that your so the question then becomes, is g of x an even or is it an odd function, right? You can ask that question. So it's not an even function, right? Because even functions have to be symmetric when you have the y-axis. So you can also show that g is not even by saying that, well, g of -1, if you substitute -1, you're going to get -2. But if you substitute +1, you would get 2. So of course, g of -1 cannot be the same, is not equal to g of 1. So you can say that, so because of that, to see that g of x is not odd, you can note that if you substitute -3, you have -6. And if you input 3, right, you would have, the value would be 8, right? Because 2 to the third, right? So 2 times 2 times 2, that gives you 8. So g of -3 is not equal to -g of 3. Okay, so that's very much so the introduction to a piecewise function. Likewise, let's do another one. Let's see if I can. Okay, so I'm just going to use a different document now. So f of x and let's make the constraints x plus 5. Okay, so it's going to be x plus 5. Let's say if -9 is less than or equal to x, and also less than or equal to -3. All right, and then we can do 2x squared minus 1. And let's say -3 is going to be less than x. And that's going to be less than or equal to 2. And we can add -x over 2. The constraint will be if x is greater than 2. All right, so the problem here is let's find the domain and the range of f. Well, first of all, for the domain and range, we need to see that f is, we're saying that f is defined for all x greater than or equal to -9. So that means the domain has to be -9 and it goes to infinity. So anything from -9 to infinity, remember when you use set notation, this is the constraint. Okay, we ended up with a parentheses because it just keeps going and going. And of course, we're really talking about positive infinity, right? So the other thing is you're going to see if you were to graph this, you can use the graph as an aid, but you can, to find the range, you can find the range of each piece, and you can graph y equals f of x. And if you graphed it all, you would have, well, x plus 5, and then 2x squared is going to look like a sort of like a parabola, and then you'd have -x over 2. So if you did graphing, you would have something called what we call open circles that mark the points that your graph approaches, but it never quite gets to that point, right? It never quite reaches that point. And of course, the solid circles mark points that are actually on the graph. So you can, I actually have an example where you can, because I graphed this earlier, and it would look like this. Let's see if I can put it in. So this is the graph of the function. Okay, as you can see, right, some of them have open circles, right? There are parts that have open circles, others have the closed circle, which means that those are points on the graph. All right, so that being said, you can see that f, by the way, appears to, if you look at it, it's continuing downward, forever downward. And because f of x is negative x over 2, because it's saying that its x is greater than 2, the piece has a range that's negative infinity to negative 1, right? So the lowest point on the middle piece is going to be 0, negative 1. Okay, so if you've done range before, you know where I'm coming from on this. So for another issue here is we're going to talk about continuity. So loosely speaking, and this is not a rigorous definition, but I'm just kind of throwing it out there. A function is continuous if you can draw the graph of the function between any 2 points without lifting your pen or pencil from the paper. If a function is not continuous, then obviously we say it is discontinuous. How creative of us, right? So this is how you should approach that, okay? And that's very important because if you start talking about things in calculus, such as the continuity of a function of a piecewise function, you can approach it from, if you've done limits, those of you who are watching this and you've done calculus, you know what I'm talking about, the limits, and you can analyze it that way. So I think this pretty much should clear up a very basic definition of a piecewise function, but I want to end it by doing a little bit more, some more problems. So let's see if I can do. So the applications of piecewise function, you might see them in, well, you see them in word problems often that involve more than one constraint, more than one variable. But let's do one where you have to, let's let f of x, let's make it 3x plus 5. And only if x is less than negative 3. And then 7 minus 4x we could do. And if x is greater than or equal to negative 3. All right, fair enough. So we need to find, if we were to say f of negative 10, well, in this case, because negative 10 is less than negative 3, we need to use our first function, which is our first constraint, which is 3x plus 5. That's 3 multiplied by negative 10 plus 5. So that's negative 30 plus 5, which gives you negative 25. Okay? And that is an example of how you would apply that. Okay? Another approach you can do, this one is, let's do one where you don't have real numbers. Okay? So let's do f of z. And we're going to say f of z is z to the second, z squared. If z is not real, Notice I'm using the R for the set notation for real numbers. And we're going to say that it's z plus 2 if z is real. All right, fair enough. So then with these constraints, let's find, what if you had a problem that said f of I, imaginary or complex, plus f of 1 plus f of negative 1 plus f of negative I. Well, in this case, right, you've got a couple things going on here. You should know by now. If you don't, again, this video is not for you then. You should know that I is not a real number. That's why we call it an imaginary number. It's the opposite of real. So because I is not a real number, you have to use z squared. So that means I squared. Now, if you're familiar with the imaginary numbers, you know very well that I squared is negative 1. So let's do that. So f of I means I squared, which is negative 1. All right, moving further ahead. Now we have f of 1. Well, 1 is a real number. So that means you need to use z plus 2. So 1 plus 2 is 3. So we have f of 1 becomes 1 plus 2, which gives you 3. Then you have negative 1 is also a real number. So you still use the z plus 2. So now you have f of negative 1 and that goes negative 1 plus 2, which gives you 1. Okay, and finally, negative I is not a real number, which means we need to go back to the z squared. And so we have negative I squared. So f of negative I is going to yield the negative I squared, right? So that's negative 1. All right. And finally, well, now you just plug in the values, right? We have negative 1, and you add them. You have negative 1. You also have 3. You have 1, and you have plus negative 1. So your final answer should be 2. Okay, and you've just evaluated the expression. Well, the piecewise function, I should say. All right, so if you have any questions or comments, please leave them in the comment section below. If you find this video useful, as always, as they always say, subscribe to my channel, up to you. And I will continue to post videos. In my next video, I might do, I'm not sure yet, but I might do evaluating the continuity of a piecewise defined function, but that's more of a calculus topic. And so I might put it in my calculus series. All right, thanks for watching.